In the last video, I hope I showed you how to create the derivative of the 6 primary inverse trigonometric functions, inverse sine, inverse cosine, and so on, using implicit differentiation. I'm going to walk you through a couple of examples, and I'll show you 2 ways to do that. And hopefully you understand what I mean by more complex derivatives. Here we go. So we're trying to find the derivative of inverse sine of 3x plus 2. So we'll do the longer way first, and then we'll use the, hey, I know a rule, let's use our rule way second. So we can actually just approach this the way we did inverse sine of x by taking sine of both sides. So sine of y is equal to 3x plus 2, which means, oh, that's super easy. I can just do derivatives. The derivative of sine is cosine. And if the input of cosine is a function like y, we'd have to use the chain rule. So we'd multiply by the derivative of y. I call that chain rule, but you should know that's also implicit differentiation. The derivative of 3x plus 2 with respect to x is just 3 plus 0. I'll write 3. It's a long day. I'm struggling. dy dx is equal to 3 over cosine of y. So we don't want to leave things with cosine of y. We started out with arc sine had an input of 3x plus 2. I guess I'll erase my triangle later. Okay, and so what's the angle named? It is named y, and we were told that sine of that angle y was 3x plus 2. So we can say this side opposite is 3x plus 2 divided by the hypotenuse. We might as well make that 1, make our lives easier. Oh no, this is getting scary. Okay, so this other side leg is going to be 1 squared, just 1, minus 3x plus 2 squared. Because it'd be this 3x plus 2 legs squared plus this leg squared should give us 1 squared. Okay? That's actually good to go. Can you take cosine of y? You sure can. That's this ugly square root stuff over 1. So dy dx is equal to 3 over, oh no, not cosine of y. Let's write what cosine of y is equal to. The square root of 1 minus 3x plus 2 squared. And extend. Okay, so that actually might be easier if you forgot the derivative of inverse sine of x. Or maybe you could say inverse sine of something, I don't know. So if you go back and look that up, if y is arc sine of something, then y prime is 1 over 1 plus that something's, no, that's inverse tangent. Square root of 1 minus that something squared, and then you'd have to multiply by chain rule du dx, the derivative of that input. Okay. So we can think of this, okay, so y is inverse sine of 3x plus 2, so we'll use our rule. Let's pretend like we're starting over and this stuff's in our head. Y is equal to arc sine, squeeze that in, of 3x plus 2. And so, let's use the same notation. dy dx is equal to 1 over the square root of 1 plus, and then it's not x squared, it's the input to inverse sine squared. What's the input to inverse sine? 3x plus 2. And, that was not a plain old x. We need to multiply by the derivative of 3x plus 2 using the chain rule, 3. Oh, she'll get it together. How about a subtraction sign? I know, you guys caught that. So hopefully you can see we're getting the same derivative in either case. I don't know which one's easier for you. You may want to practice both because these inverse trigonometric derivatives don't come up a lot. and all kind of feel the same. Right? Lots of ones, lots of squaring, and lots of rational functions. Okay, should we do this the long way or the short way? How about the short way first? If you found the pattern in the inverse trigonometric derivatives, inverse cosine has almost the same derivative as inverse sine. They just differ by a negative. So, the derivative of inverse cosine is negative 1 over the square root of 1 minus the input squared. What's the input to inverse cosine? 2x cubed. Ooh, that's a function. We need to multiply using the chain rule by the derivative of 2x cubed, which is 6x squared. You could rewrite that with the 6x squared in the numerator if you want. Maybe let's do that and make things pretty. There we go. All right. If you wanted to do this the longer way by taking cosine of both sides, I'll do that for this last one, and then I'm going to start doing things the short way. Okay. So cosine of y is 2x cubed, which means when we draw a triangle, for the angle y, cosine is 2x cubed, I guess over 1, and this missing opposite side is 1 minus 2x cubed squared, using Pythagorean theorem. So the derivative, back to the left, of cosine of something is negative sine of something. Our something is some function named y, so we also have to multiply by the derivative of y. And the derivative of 2x cubed is 3x squared times 2, 6x squared. So y prime is going to be negative 6x squared, I like my negatives in the numerator, over sine of y. Look at your triangle, we already have the angle y. Sine of the angle y is that square root stuff over 1. So I'll just replace sine of y with the square root of 1 minus 2x cubed squared. All right, here we go. Just an example using the rule. You know it. We used it in the last example. The derivative of inverse cosine of something. Negative 1 over the square root of 1 minus the input squared. Okay. So inverse cosine has a derivative negative 1 over the square root of 1 minus the input squared. Almost the same derivative as inverse sine. What was the input to inverse cosine? Tangent, which has a rate of change of secant squared. So I guess if I'm taking the AP test and this is multiple choice, it's going to look like negative secant squared x over the square root of 1 minus, maybe it says tangent squared x inside that radical. Ooh, do you remember the rule for the derivative of inverse tangent? If you don't, you can just take tangent of both sides and have tangent of y is 3 minus 5x. However, I do remember, I do this probably a lot more than you, and the derivative of inverse tangent of something is 1 over, the order doesn't matter, 1 plus the input squared. You could have also had 1 over the input squared plus 1. Let's see, what's the input to inverse tangent? 3 minus 5x, which has a rate of change, a derivative of negative 5. So I'm just going to write a negative 5 up here instead of 1 times negative 5. Oh, how are you going to find the equation of the tangent line to secant at pi thirds? So first, we'll just use the derivative of secant that I know you all memorized. 1 over the absolute value of x times the square root of x squared minus 1. Okay, so at x equals pi thirds, use good notation, y prime is equal to 1 over the absolute value of pi thirds, just pi thirds. It's the square root pi thirds squared minus 1. Ick. Well, maybe not. I'm probably not going to have to evaluate this. So let's see, what am I going to do? I'm going to make this look slightly better, but not a ton. I'm going to write this as 3 over pi, let's see, times the square root of pi squared ninths minus 1. That still doesn't look very good because we have a complex fraction. And so I am going to multiply the numerator by 3 and the denominator by a different version of 3, the square root of 9. And so we get 9 over, I'm actually not going to do the square root of 9 times the pi. I'm going to leave the pi alone and multiply down here. So pi squared minus 9. That actually looks fairly decent. If you need a numerical value, that's going to be a calculator thing anyways. Okay, well, our job is not to find the slope of the tangent line, but the equation of a tangent line. Well, I have a slope, I have an x value, I just need a y value. So, let's see, using x equals pi thirds, y is equal to inverse secant of pi thirds. Oh, inverse secant of pi thirds. That's not normal. You're thinking pi thirds, hopefully you're thinking, pi thirds is an angle. Inverse secant has an input that's a ratio of sides. So that's not going to be a common number either. We're just going to have a really, really ugly tangent line. Since we're doing something new, we're going to write tangent line. That's a new idea. I don't mean you've never seen tangent line. I mean in this problem. So that's going to be y minus the y value, which is inverse secant of pi thirds, which is equal to the slope, 9 over pi times the square root of pi squared minus 9 times x minus pi thirds. Okay, so that was a weird example. But good news, you'd never see this on the AP test. The reason being, you're going to be given trigonometric functions that you can either evaluate or that you have a graphing calculator for. So in either case, you wouldn't have something ugly like this.